We've got a problem and we're looking for advice. And I thought a great resource would be to tap into the cumulative knowledge of our large audience. Now, when you hear about this problem, you're not going to feel sorry for us because it's a little bit like complaining about being too rich or too muscular. The fact is, our lasers are too powerful. Now, I know, but hear me out. About 6 months ago, we did a collaborative video where we used a computer-controlled targeting and tracking system to direct a high-powered laser to destroy drones in flight. Effectively, a directed energy device. Of all the videos that we've done, I think I enjoyed that video more than any other one. It was an absolute blast. Firstly, it worked. And despite the fact that we discovered a few limitations in the system, the technology is so intriguing that we think it's important enough that we've decided to redo it and upgrade everything. A faster computer, a more sensitive, higher resolution and faster camera, and more accurate and faster mechanical tracking system. And then I bit the bullet, joined the big boys, and obtained a couple of fiber lasers. These things are truly spooky. Now, single mode fiber lasers are so good that the beam they emit is bumping right up against the physical limits of light itself. And they're fascinating enough devices that I think we may do another video soon covering some of the technology around fiber lasers. We'll cover the principles, the engineering, some of the limitations, as well as some of the near-term improvements that we're going to be seeing in these systems. We'll also cover where do you buy them, how much do they cost, and then we'll challenge a variety of different materials to the high-powered laser to show you what they can do. I think it'll be very interesting. Now, the fiber lasers that we have here are designed for an application of industrial metal cutting, like you saw in the clip. And the way they do that is the output from the laser is guided through a delivery fiber, different than the fiber that's generating the laser light. And that delivery fiber sends the light into an optical head that has several lenses in it that directs the beam down to a very, very tiny focus relatively rapidly. And at that very tiny point, it does its magic. Because the beam is coming in at a relatively sharp angle, as soon as it's melted through the metal, it continues to diverge at a relatively sharp angle, so that what hits the floor or the bottom of the machine doesn't get exposed to very intense laser light, it's not damaged. That's not how we're using this here. I've designed some optical assemblies that include beam correction optics that remove or minimize the small amount of residual aberrations that are present from fiber lasers. There's then a rough collimating lens that gets the beam relatively parallel, and then a fine focusing lens that really nails it and gets a very tight beam coming out of the end of the laser. The result is that the beam that it emits is small to begin with and continues to grow smaller for a very long distance. When compared to the previous laser that we used to take down the drones, where we demonstrated that this laser was capable of melting through steel, burning a hole in fire brick, and destroying a truck tire, the intensity of the light radiation from this source on the target is 500 times higher. And we have two of them. The result is, unlike the first laser, which tended to barbecue the targets, this should slice and dice them. And that's where we're starting to get into a problem. Because if I were to turn one of these lasers on, within less than a second, it would burn through the side of this building and into our truck parked behind the building. Not good. So we need something to stop the beam. It's not practical for us to turn the power down because that kind of undermines the purpose for the laser. If we had millions of dollars, we could build a specialized facility for this, or if we had access to a salt mine, no problem. But we don't have access to either resource at this point. What we need is something that will protect the building from the high-intensity laser radiation. Now, when the laser is scanning very rapidly, we're probably okay. But if the hardware, for whatever reason, locks up, or the computer glitches and the beam doesn't move, or if the beam hits a target and is almost instantly destroyed, there's nothing between the laser and the back wall, and we could do damage. We need something that can block the laser radiation for at least a few seconds, preferably more, but at least a few seconds, so that the computer can override and turn off the lasers, or we can hit the kill switch and stop them. The material that we need has to have several properties. It needs to block the beam, hopefully for a long period of time, but at least a few seconds. It should be something that is absorbent rather than reflective. We don't want to send the beam back at us. In addition to that, we need something that does not emit toxic gases when the laser hits it, something that doesn't burst into flame, and something that is at least somewhat portable. We could build a huge multi-ton stone wall in order to block the beam. But the problem with that is that between tests or when we're done with the video, it's going to be a real hassle to remove it. Finally, it should be something that's reasonably available and hopefully cheap. I became aware of how difficult this challenge was going to be when I started testing some materials. I started out by testing some drywall. What I did is I built a small test stand with a bunch of bricks and concrete blocks behind it, thinking that drywall is relatively cheap, it doesn't absorb the laser light, and if it lasted a second or two, even if I had to put a couple of sheets in order to block the laser, I'd be good. So when I set this thing up against the backdrop and then fired the laser at it, I looked sideways and timed it. And I got about 1/4 of a second. Not very good. So I would end up needing to use as many as 8 or 10 individual panels against an enormous area like this. We're talking 30 or 40 sheets of drywall. This really isn't practical. So then I tried plywood, and it worked remarkably better. 3/4 inch plywood stopped the beam for about half a second, maybe a little bit longer. So that might be a possible option, except when the laser hit the plywood, it instantly started on fire. And you can imagine if you had several layers of burning plywood underneath the intensity of the beam, some of those fires are not going to be accessible to us, and we're going to end up with a fire department here. So that's really not a good option. Then I thought, what about water? What if we just took a bunch of blankets, soaked them in a tub, and hung them up against the back wall? Maybe that would do it. Doesn't work, because what happens is that the beam, I don't know if you can see this very clearly, but we can probably give some close-ups later on. I tried towels, blankets, multiple layers, even hot pads from the kitchen. And the beam is about 1 millimeter in diameter at the contact point. So the amount or volume of water that's going to be evaporated or boiled away to carry away the heat is so small that within milliseconds it's gone. And there's not enough time for the surrounding water to be able to work its way into the hot spot. And so it punched holes in the cloth faster than you could time. This wouldn't work either. And then I thought, oh, I got a bright idea. How about using Pink Panther fiberglass, the same stuff that you use as a thermal insulator in your home? The idea being that even though it's not very massive, it's very thick and has millions of little tiny glass fibers, which could potentially redirect or bounce the beam around inside of the material, trapping the heat. Well, it didn't work. Within well less than a second, it punched a hole right through the middle of the material. I don't know if you can see the light through here, but it was like rain on cotton candy. It just dissolved it. And it was kind of interesting as soon as we turned the beam off, the hole continued to enlarge. The glass was so hot that it continued to melt even after the beam hit it. So this wasn't an option either. Now the back wall that we used for the test was made up of these concrete bricks. And as you can see, this side of the brick is unperforated. It did well. But the side that was facing the laser behind the test samples has a bunch of craters of molten brick or stone that were formed wherever the laser hit it. Now, as I explained, we're not going to use a large brick wall. It's just too massive. The only reason I'm actually showing you this is to give you an idea of the magnitude of the problem that we're dealing with. This is a brick, and still, you can see what happens to it. So, what we're looking for is a suggestion or a solution, and if you have any good ideas, put them in the comments section below the video. Because as I do with every video, I read all the comments and I try to respond to as many of them as possible. And if you come up with a good idea or a good solution and you're willing, we'll even give you credit when we do that video. I think that really would help us out a lot. In addition, if you like the kind of stuff that we do on this channel, the stuff we've done in the past, the stuff we're doing now, the stuff that we're going to be doing, please do us a favor and take a few seconds, it doesn't cost a penny, subscribe, give us a thumbs up, because it's really sort of a push and pull between YouTube's algorithms and our content. The more that the algorithms are influenced to increase the distribution of our videos, the larger we get, the more we can afford to do, and the more frequently we can do it. So we really appreciate it if you just take a few seconds to do it. It really helps us out. And as I said in the beginning, I'm not complaining. This is a fun problem to deal with. So hopefully we'll find a good solution to it. In any case, I want to thank you very much for watching. Stay safe, have fun, and we'll see you soon.